Hi everyone, welcome to the second video on sequences versus series for Math 1452 at Texas Tech University, which is Calculus 2. So in our last video, we talked about the basics of what is a sequence and what is a series. And in this video, we're going to be looking at some concrete examples of a sequence and a series and determining their convergence. So first off, we're going to look at the sequence a sub n from n equals 1 to infinity with our general term an as 1 over 2 to the n. So remember here that this curly brace notation is just the general way to denote a series, and that this a sub n is called our general term. So for a series, evaluating if these sequences converge or conversely, if they diverge, so a series will either converge or diverge, then what we need to do is all we do is take the limit of the general term. Very quick and simple. So to do this, we're taking the limit as n goes to infinity of 1 over 2 to the n. And this may be something that you were comfortable taking a limit of before this class, but just to kind of use our new strategy of the tower of power, we can compare the growth of the numerator and denominator. So here, the numerator has no growth. And here, the denominator does have growth. So what I mean by that is that when we look at just think about the function 1, well, that's a horizontal line, and that has a slope of 0. So no matter if n changes and if n increases, that 1 is going to stay the same. However, in our denominator, when we look at 2 to the n, well, when n equals 1, that's 2, and then we get 4, and then we get 8, and then we get 16, and this is just going to keep getting bigger and bigger. So this does have growth. So we can look at our tower of power, which compares how common functions grow. And you can see that the constant value 1 isn't even on the tower of power, and that's because it has no growth. The slope of that function is 1. So that means that whenever we evaluate this limit, that 1 is going to stay the same, but my 2 to the n is going to keep getting bigger and bigger until it's infinite, which tells us that this limit is 0. So we were able to evaluate this limit using the tower of power. And now we say, okay, well, what was my conclusion here? So remember that a sequence converges if this limit exists and is finite. So this limit is 0, so that exists and is finite. So our conclusion here is that the sequence converges. Okay, so our conclusion there is the sequence converges because that limit exists and is finite. So determining convergence of a sequence can be a short and sweet. Just take the limit and see if it's finite or not. However, when we look at series, so for example 2, we're looking at a series with the same general term. So you can see that this general term is the same. And again, this summation uppercase Greek sigma is just our normal notation for series. And when you see a sigma, you think summation. So to determine if this sequence converges, we need to find the partial sums. So the first partial sum is just plugging in and adding up to k equals 1. So that means that we're just adding up 1 over 2 to the 1, which is just 1/2. There's no other things to add because there's only one term in our summation. Next, for S2, we're going to add up the first 2 terms in our summation. So that's going to be 1 over 2 to the 1 plus 1 over 2 squared, which is 1/2 plus 1/4. And so in order to do anything with these partial sums, we need to simplify them completely. So to do that, we need to get a common denominator between these fractions of 4. And we see that this is going to be 3 over 4. So just to make it more clear what our partial summation is, I'm just going to circle these as we go. So next, we have our S3, which means that we're adding up the first 3 terms in my summation. So that's going to be 1 over 2 to the 1 plus 1 over 2 squared plus 1 over 2 cubed, which is 1/2 plus 1/4 plus 1/8. So again, to add these, we need to find a common denominator, and that's going to be 8. So we have 4 over 8 plus 2 over 8 plus 1 over 8, which is 7 over 8. Okay, lastly, I'm going to go ahead and do S4. So that means we're adding up the first 4 terms. So that means we're adding up 1 over 2 to the 1 plus 1 over 2 squared plus 1 over 2 cubed plus 1 over 2 to the 4th, which is adding 1/2, 1/4, 1/8, and 1/16. So again, our common denominator here is going to be 16. So 8 over 16 plus 4 over 16 plus 2 over 16 plus 1 over 16 all adds up to 15 over 16. So I will pause here for 1 second and have us think about how we can relate the subscript of the partial sum we're in with what's happening whenever we add up all of these fractions. So we can immediately see, okay, well, for S1, my numerator is 1, and that's the same. And my denominator is 2, and that's 2 times 1. So next, let's kind of think about S2. So now, well, my denominator is 3, and that's 1 more than 2. And my denominator is 4, and again, that's 2 times 2. And let's go to S3 and think about this. So now, to get from 3 to 7, there's not really a clear pattern here. But to get from 3 to 8, we can see that we went from 3 to 8 because that was 2 cubed. And we can see that also in S4, we got our denominator of 16 because that was 2 to the 4th. So one thing we can see is that all of our denominators have that power of 2 that corresponded with the subscript of SK. So that means our denominator for SK can be 2 to the K, because that's the denominator in all of them. And there wasn't a necessarily clear pattern about how this numerator related to the subscript of S. But what we can notice in those circled numbers is that the denominator was always 1 more than the numerator. So that numerator always was that denominator minus 1. So we can just repeat that denominator minus 1. And now this is something that we can take the limit of. So I will pause here and say that finding this general formula for SK is very difficult and really does take some practice to get used to. So don't expect yourself to be able to immediately see this. You may be someone who needs a little bit more time and a little bit more examples to kind of get the feel for how to write this partial sum. So now we're going to evaluate this limit. And what I'm going to do is I'm going to simplify this expression as 2 to the k over 2 to the k minus 1 over 2 to the k. And then I'm going to simplify that first fraction as 1 minus 1 over 2 to the k. And so that we know that the limit of any constant is just going to be 1. And so now, whenever we evaluate the limit of 1 over 2 to the k as k goes to infinity, we can see that that's actually the same limit that we did in example 1. So that's going to be 0. And 1 minus 0 here is 1. So that's our limit. It's 1, it exists, and it's finite. So we remember, we look back up, okay, when does a series converge? A series converges when, again, that limit exists and is finite. So therefore, our conclusion here is that the series converges. Okay. So we're going to go ahead and go on to example 3. So for example 3, we are changing our general term here and looking at a new sequence with a new general term. So what we're going to do is remember that this is just the way that we write series, and the series are our list. And we have that this AN is our general term. So remember that to evaluate the convergence of a sequence, all we do is we look at the limit as n goes to infinity of that general term. So the ln of n over n squared. So to evaluate this limit, we are going to use our tower of power. So remember that up here, our tower of power, our numerator down there is ln of n, and our denominator is the square root of n. So because the square root of n is bigger than the ln, than the natural log, we can immediately say that this is 0 by the tower of power. So your instructor may or may not have shown you the tower of power. So in this video, I'm going to say this is 0 by the tower of power. However, if your instructor wants you to show additional work or give additional reasoning, you should go ahead and check with them to see how much work they want you to show whenever you're evaluating if a sequence converges or not. So for us, I'm just going to say that follows by the tower of power, but make sure to check with your instructor about how much work they want you to show. Lastly, we're going on to example 4. So again, this is a series which has that uppercase Greek sigma. And again, we have the same general term as example 3. So for a series, to determine if a series converges, there's a typo on my sheet. I will make sure that your sheet does not have this typo. So to determine if this series converges, we are going to look at the partial sums. So to determine if the series converges, we're looking at the partial sums. So for S1, that means we're adding up the first term. So we are going to look at ln of 1 over 1 squared. And so in this case, we know that the ln of 1 is 0. So this is just 0 over 1, which is 0. For S2, we're going to add the first two terms. So that first term was 0. And then we're going to add up ln of 2 over 2 squared, which I'm just going to simplify as ln of 2 over 4. And again, just to make sure I can know what these sums are, I'm just going to circle them once I get them. For S3, we're going to look at 0 plus ln of 2 over 2 squared plus the ln of 3 over 3 squared, which I'm just going to simplify as ln of 2 over 4 plus ln of 3 over 9. And again, we need to make sure that we're going ahead and adding these fractions by getting that common denominator. And so my common denominator here is going to be 4 times 9, which is 36. So that's going to give me 9 ln of 2 plus 4 ln of 3 all over 36. And again, I'm just going to circle this. And lastly, you can write out S4 on your own, but I'm just going to tell you what that final answer is after we add the fractions. This is going to be 36 ln of 2 plus 16 ln of 9 plus 9 ln of 4 all over 144. Okay. So at this point, again, we're trying to find a pattern that corresponds with our subscript. And so you may have a better natural talent at this than I do, but at this point, to me, there's no clear pattern of how to write that general formula. So in this case, I would look for additional strategies, and there are additional strategies that are going to come in the later sections of the textbook, specifically 8.2 through 8.6, as well as in the infinite series test worksheet found in the same place that you found this one. So we're going to have a lot of different strategies to determine if series converge, and that is what the rest of the chapter is on. But for now, we hope that this was a good introduction to sequences and series and how they're different. So we hope this helps, and good luck.